The remainder of this chapter deals with types of reactions. And the first type we'll be dealing with has to do with reactions in solution. Let's consider this apparatus where we have electrodes dipped into water, a salt solution, and a sugar solution. When we throw the switch in each one of these, do we have a complete circuit? Can you make a prediction as to whether we have a complete circuit and the light bulb will light up when we throw the switch? Or will the light bulb not light up? So the first example would be that of pure water with nothing dissolved in it. The second would be this salt solution of sodium chloride. And the third would be this sugar solution. Make your prediction. Now watch this video. Both of these beakers contain pure water, and as you can see, neither conducts an electrical current that would light the light bulb. Now let's add some sodium chloride, NaCl, to one of these beakers and check the conductivity again. We can definitely see that the solution of sodium chloride is an electrical conductor. Now let's add some table sugar to pure water and check its conductivity to see if it carries an electrical current. It does not. A solution of table sugar in water is not an electrical conductor. Let's see if we can understand why the salt solution did conduct an electric current, whereas when we put sugar in water, it dissolved, but there was no conduction of an electric current. So why is this? To understand, we have to look at, first of all, the water molecule, and then at sodium chloride. The water molecule, as you well know, is two hydrogens attached to an oxygen. But what you might not know is that one side, the oxygen side of this molecule, has a slight negative electrical charge. And the hydrogen side of the molecule has a slight positive charge. This makes all the difference in terms of how water dissolves substances. Sodium chloride, on the other hand, is a solid substance where sodium and chloride ions are locked in a crystal lattice with very powerful attractions between the sodium ion and the chloride ion. Sodium chloride has a very high melting point, around 800 degrees Celsius. And yet, this whole crystal, falls apart easily in water. It breaks up into sodium ions and chloride ions. What is there about water that allows it to dissolve sodium chloride? Let's take a look at this particle view of it. We saw how the water molecule had a negative end, the oxygen side, and a positive end, the hydrogen side. Well, that makes water something called a dipole. If the positive side of the water molecule approaches a chloride ion, it sets up an attraction, and the chloride ion becomes surrounded with the hydrogen side of several water molecules. The sodium ion has a positive charge, and it is attractive to the negative side of the water molecule. So water molecules surround the sodium ion, and these are very powerful attractions that allow the sodium ion and the chloride ion to be pulled away from the sodium chloride crystal. So now we have ions floating around, each ion surrounded with water molecules. We call that hydrated ions. Either a hydrated anion if it's a chloride ion, or a hydrated cation if it is a positive sodium ion. And the solution is filled with ions. And this is why a sodium chloride solution carries a current, because these floating ions are able to be attracted to the different electrodes and undergo changes at the electrodes that allow electrons to flow from one electrode to another electrode. And that completes the circuit, and the light bulb lights up. A substance that dissolves in water to produce significant free-floating ions is called an electrolyte. If an ionic compound is not water-soluble, It cannot be an electrolyte. Now what about sugar, you ask? Why doesn't it conduct an electrical current? Let's take a look at it. The sugar molecule, drawn here in a space-filling model and over here as a drawing, has a lot of oxygen-carbon bonds and oxygen-hydrogen bonds. And every one of these oxygens can be attracted to a water molecule, because every one of these oxygens has a slight negative charge that is attractive to the positive side of the water molecule, the hydrogen side. It also has hydrogen atoms attached to oxygen, which gives them a slight positive charge, and that would be attractive to the negative side of the water molecule. So when sugar dissolves in water, what we see is this, that the entire molecule becomes surrounded with water molecules. The oxygens are surrounded by the positive side of the water molecule, and hydrogen atoms are attracted to the oxygen side of the water molecule. But there's enough hydration going on in this entire molecule that allows the molecule to be pulled away from the crystal lattice, and the sugar dissolves very well. But there are no ions. And without ions, there is no conduction of an electrical current. It is not an electrolyte because there's no ions. So we've seen how sodium chloride breaks up into ions when it dissolves in water and is an electrolyte. Here's another electrolyte, sodium phosphate. It too breaks up into ions when it dissolves in water. But is there a chemical reaction that we can write that represents the sodium phosphate dissolving in water? How would we express that? Well, first of all, we'd have to write the compound. Let's see, sodium we know is Na+, and phosphate we've memorized as PO4 3-. So the formula for sodium phosphate, you're going to need 3 sodium together with 1 phosphate to make Na3PO4. Now you're going to put this in water, and it's the way the question is wording, it's telling you that it's going to dissolve in water. There are many ionic compounds that are not soluble in water, and you could not write an equation in which they break up into ions because they scarcely do. So sodium phosphate, if we put it in water, remember the water is going to surround the sodium ion, the water is going to surround the phosphate ion. We do not show the water in the equation. We just show the ions that form. So we're going to form, when this starts breaking up, sodium ions, and we're going to form phosphate ions, PO4 3-. And we're going to have, in order to have a balanced reaction, we're going to have 3 sodium ions to balance the 3 in the formula. So here is the equation for sodium phosphate dissolving in water. Now, what's the concentration of sodium ions in a 0.3 molar solution of sodium phosphate? So this solution is 0.3 molar in sodium phosphate, and it breaks up, and for every 1 formula unit of sodium phosphate, we have 3 sodium ions being produced, floating around in the water. So the concentration of sodium ion is going to be 3 times your starting molarity of the sodium phosphate, because it's a 1 to 3 relationship. Again, stoichiometry. So that's going to now be 0.9 molar in sodium ion. And the phosphate, of course, is only 1 phosphate on each side, so the phosphate is going to be 0.3 molar. Write the molecular equation when solutions of iron 3 nitrate and barium hydroxide are mixed. Well, we have to write, first of all, the formulas for iron 3 nitrate and barium hydroxide. So we start with a solution inventory. Here's iron, ion. Here is nitrate. Here is barium, ion. And here's hydroxide. So when we make formulas from these, iron nitrate is going to have the iron and the nitrate combined. And we're going to need 3 nitrate for every 1 iron, because iron is 3 plus and nitrate is only -1. So we need 3 of the nitrate. And for the barium hydroxide, obviously we're going to need 2 hydroxide ions for every 1 barium. So when we write out the formulas, we should see something like this. 3 nitrates for 1 iron and 2 hydroxides for 1 barium. What happens when these react? Well, this kind of reaction in ionic solutions is called a double displacement reaction. And what really happens is that the ions switch partners. The iron, which was connected to the nitrate, goes off and bonds to the hydroxide. The barium, which was connected to the hydroxide, goes and bonds to the nitrate. So for our reaction, we would write an arrow and then the new iron compound that formed, iron hydroxide, and the new barium nitrate that forms. However, this is not a balanced reaction yet. If you notice, we have 3 nitrate over on this side and 2 nitrate on the product side. Likewise, the hydroxide is not balanced, 2 and 3. So we're arbitrarily going to start with, say, balancing the nitrate. You could just as well start at hydroxide, but here I have 3 nitrate and over here I have 2 nitrate. So what would be the smallest common number between 3 and 2? Well, I think that'd be a 6. So if we put a 2 right here, that will give us 6 nitrate. 2 times 3 is 6 nitrate. And if I go over here and put a 3 in front of this barium nitrate, then I will have 6 nitrate again. 3 times 2 is 6 nitrate. Well, what about the hydroxide? One side I have 2, the other side I have 3. It's going to be the same thing. 6 will be the common number. So I'm going to put 3 over here to give me 6 hydroxide, and I'm going to put 2 over here to give me 6 hydroxide. And incidentally, the iron and the barium fall into place, and they are now balanced as well. So here's our balanced molecular equation. The one thing that is not showing up here is, are the new compounds that form, are they soluble or are they not soluble? How can we tell what the status is of the products? In fact, what we really need to do is go in and put in the phase for each one of these. The iron nitrate, we know, is in solution because the question says when solutions of iron 3 nitrate and barium hydroxide are mixed. That is telling us that iron nitrate and barium hydroxide are soluble. And as soluble compounds, what do we do? How do we write that? We would write a parenthesis and we'd put a Q to represent the state for each one of these, AQ. Yeah? Now, what about the products? How do we know if iron hydroxide is soluble or not? How do we know if barium nitrate is soluble or not? So it turns out that there's going to be a solubility table made available to you that will help answer questions like this. In this table, you have a listing of compounds with ions that are usually soluble, and then the exceptions. So ammonium, for example, all the compounds with ammonia ion are going to be soluble, and no exceptions to that. Sodium, potassium, and lithium, almost all of those compounds containing sodium ion potassium, or lithium are going to be soluble. There are a few lithium salts that are not soluble. Nitrate, all the nitrates are soluble. What about chloride, bromide, and iodide? They all tend to be soluble, but with three big exceptions: silver, mercury, and lead. These will form precipitates with chloride, bromide, or iodide. Acetate ion is mostly soluble, except for silver acetate. And chlorate, again like nitrate, no exceptions. Sulfate, almost all are soluble, except the alkali earth elements, barium ion, strontium, calcium, as well as lead, mercury, and silver. Sulfates are not soluble. Also, on this side of the table, we have compounds that are usually not soluble if they contain carbonate, phosphate, hydroxide, or sulfide. Such compounds containing these ions are generally not soluble, and the exceptions right here: ammonium, sodium, potassium, like that. Let's look up our products, which were iron hydroxide and barium nitrate. Well, first off, we know the barium nitrate is soluble because all nitrates are soluble. As for the iron hydroxide, you see hydroxide is in the list of ions that are usually not soluble in compounds, and hydroxide is one of them, and not an exception with iron hydroxide either. So the iron hydroxide is not going to be soluble. It's going to be a solid. It's going to precipitate out. So when we would write the equation, this is how we would write it. Aqueous for the reactants. S in parentheses meaning solid, precipitate for the iron hydroxide, and again aqueous for the barium nitrate. And this is called the molecular equation. Another way we can write this equation out is the total ionic equation, where we show all the species as ions except the compound that's not soluble. So if we do that, we would get a total ionic equation that would look like this. Here's our ion. We have two of them. Here's our 6 nitrate. 2 times 3 nitrates is 6 nitrates. Here's our 3 barium ions and our 6 hydroxide ions. And the iron and the hydroxide react to give iron hydroxide as a solid. So this is called our total ionic equation. Another way that we can write an ionic equation out is something called the net ionic equation. We would do that if we start from the total ionic equation by canceling out the ions that are spectators. In other words, they are merely watching the reaction. They are chemical voyeurs, so to speak, and we want to get them out of there, right? So what ions are not participating? That they exist in the reagent side and they exist in the product side. It looks like barium ion exists in both places. It looks like nitrate exists in both places. The iron and the hydroxide do react, so we would not cancel those out. So the net ionic equation, canceling out the ions that do not react, the so-called spectator ions, gives us this equation: 2 iron plus 6 hydroxide yield 2 iron hydroxide. And we have to reduce that down by dividing each term by 2. So we'll get iron plus 3 hydroxide yields iron hydroxide. And that is what we call the net ionic equation. So let's try another one. If solutions of lithium nitrate and ammonium phosphate are mixed, what is the ion inventory and what are the molecular, total ionic, and net ionic equations? Well, first of all, we know lithium is in the alkali metal group of the periodic table, and it has a +1 charge. For nitrate, ammonium, and phosphate ions, we have memorized those, and we know what the formulas of those polyatomic ions are. You've got to learn these polyatomic ions. So if we write out these ions correctly, it will help us write out the compounds that these ions form. So lithium combines with nitrate, and that is simply LiNO3 in the aqueous phase because it's a solution. And ammonium phosphate is NH4 3PO4. We need 3 ammonium ions for every 1 phosphate, because ammonium is +1, phosphate is -3. So here are our initial reagents that are being mixed together. And now we're ready to write the molecular equation by having the ions switch partners. Lithium would go with phosphate and ammonium would go with nitrate. So we can write that out, and when we do that, we'll have 3 lithium nitrate and 1 ammonium phosphate forming lithium phosphate and 3 ammonium nitrate. How do we know that lithium phosphate is a solid? You see it's marked here solid. How do we know ammonium nitrate is aqueous? Well, when we write these compounds out, we have to check their solubility in the solubility table. If we look at the position of lithium in this table, we see most compounds with lithium are soluble. But there are some salts that are not soluble. It doesn't specify which ones. But over in this column, the phosphate is listed under ions in compounds that are usually not soluble, and lithium is not an exception. So we can gather from this that lithium phosphate is insoluble. It is not soluble. It is not going to form ions in solution. So that's why we can write an S stating this is lithium phosphate in the solid form in this compound. Now, ammonium and nitrate ions, if we look again at the table, all ammonium compounds are soluble, no exceptions. All nitrates are soluble, no exceptions. So that's a clear indication that ammonium nitrate is going to be soluble in water and have the designation AQ. Now we have to write the total ionic equation. And we do that by breaking each one of these compounds up into ions, except for the lithium phosphate, which does not dissolve and does not break up into ions in solution. It is insoluble. But these other 3 compounds, all in the aqueous phase, are all existing as ions surrounded by water molecules. So if we break these up, we'll end up with a total ionic equation that looks like this. First of all, 3 lithium ions, because we have 3 lithiums in here, and we have 3 nitrates. So 3 lithium ions and 3 nitrate ions. For the ammonium phosphate, notice we have 1 formula unit of ammonium phosphate. But within that 1 formula unit, you'll see 3 ammonium ions and 1 phosphate. So we would write 3 ammonium ions and 1 phosphate ion. Here's our lithium phosphate, which we know is not going to break up into ions. And for the ammonium nitrate, that's going to break up into 3 ammonium ions and 3 nitrate ions. Now we're ready to write the net ionic equation. And we do that by determining which ions are spectators. In other words, these are ions that are not combining to form any compound. There are ions in the reagent side, they're still ions in the product side. So we're able to cancel them out, so to speak, from each side. And when we do that and take those out, we end up with the net ionic equation. 3 lithium ions and 1 phosphate ion yields lithium 3-phosphate. Okay, let's try another one. Sodium carbonate reacts with calcium chloride. What ions are present before any reaction occurs? In other words, what's the ion inventory? So I've written this in a format that you will see on a test. You just have to choose the line that represents the ions, and it can get confusing. You have to pay attention. The way I like to do these kinds of questions is to just cover up the answers so I don't get confused. And since I've learned what sodium is, what carbonate is, and calcium, then I write down the ions. I know sodium is Na+. Let me write this. Na+. And I know carbonate is CO3 2-. And of course, calcium I know is Ca2+. And chloride is Cl-. Now that I know I have to have all these ions in a particular answer, I can start going through. The first line is out because this carbonate only has one negative and not two, so that's out. Second line is looking good. Third line has a CO2 instead of a CO3 for carbonate. And the fourth line has a 2+ for sodium. So a good strategy for test taking when you have multiple choice is to work the question to the best of your ability. Forget about the answers. Don't look at them. Don't try and guess the correct answer. Write down your answer, then look at the multiple choice replies and choose the one that agrees with what you've written, if it exists. And if it doesn't, then you've got some thinking to do. So the next question, if sodium carbonate reacts with calcium chloride, what is the net ionic equation? Now, since we've already done the ion inventory, we can now take a look at the solubility chart to see if any possibility of any of the products are insoluble. So here they are. We have sodium ion and carbonate ion and calcium ion and chloride ion. We know all compounds with sodium are soluble. We know most compounds with chloride are soluble except for silver, mercury, and lead. What about carbonate? Well, let's see now. Carbonate is in our usually not soluble column, and calcium is not an exception. So there it is, telling us that calcium carbonate would form. So if we're just going to write the net ionic equation, it's perfectly acceptable to just write the two ions, the calcium ion, carbonate ion, combining to form calcium carbonate. So far we've looked at ions that combine to form precipitates. Well, there's another way that ions can combine in water to form something called weak acids. Before we tell you what a weak acid is, let's tell you what a strong acid is. Strong acids ionize completely in water. So if we let X- represent any of these 6 anions, ClO4- perchlorate, NO3-, HSO4-, I-, Br-, or Cl-, then HX, in other words HI or HBr or HCl, is a strong acid. And what that means is that if you have any of these 6 anions in water, they never combine with hydrogen ion to form HX, or the strong acid. Instead, whenever you put HX in water, it completely ionizes to form hydronium ion and X-, the anion itself. It's almost like 100% ionization. So strong acids are very, very strong electrolytes. They completely break up into ions in water. That's what a strong acid is. And again, it's just these 6 anions that you have to know, because those are the ones that form strong acids, and strong acids in water ionize completely to form hydronium ion. Now, weak acids, on the other hand, never ionize completely in water. So if Y- is not one of these 6 anions, then HY is a weak acid. And in that case, when you put HY in water, it remains as HY. Unlike a strong acid, only a tiny little bit of HY reacts with water to form a very, very small amount of H3O+. Completely different than what a strong acid does. Now, beyond that, that means that if you have a combination of ions, you may well get the formation of a weak acid. For example, here's a question: which anion reacts with a strong acid to form a weak acid molecule? By the way, this listing of these six anions that form strong acids are in the precipitation table over in a box. So I've highlighted it here. So with this question, really the question is saying which one of these anions is not one of these 6 anions of strong acids. I minus certainly is, NO3 certainly is, HSO4 certainly is, HS minus is not. HS minus is the salt of a weak acid. So if you put that together with a strong acid, it's going to form H2S. It's going to form its weak acid form. For writing net ionic equations in a question like this, what happens when we take sodium acetate and put it in water along with a strong acid HBr? Well, sodium acetate is the salt of a weak acid. It breaks up into sodium ion, that's Na+, and the acetate ion, C2H3O2-. So you have sodium ion and you have acetate ion together with HBr, and that's going to break up into H+, really H3O+, but sometimes we just shorten it and call it H+, plus Br-. So you have all these ions together. Are any of these two going to combine to form a molecule? And the answer is yes, indeed. H+ and C2H3O2- are going to combine to form a weak acid. So the net ionic equation for this is H+ plus C2H3O2- forms H C2H3O2. Funny 2 there. That's what happens when you have an anion that is the salt of a weak acid combining with a strong acid. It forms the weak acid as in the molecular form. Now what about taking nitric acid and sodium chloride? Let's do an ion inventory. We have H+, we have NO3-, we have Na+, we have Cl-. Can any of these ions combine to form a weak acid molecule? Well, the answer is no. We have H+ and Cl-, but that's not going to come together to form HCl, because HCl is one of the 6 strong mineral acids, and it never forms in water. It always is completely ionized. So this is no reaction here. When we take these 2 components and put them in water, there's just no reaction that happens. We just have these ions floating around in solution. Now it's sometimes necessary to talk about the oxidation number of elements in compounds. Let's talk about first how to calculate an oxidation number for an element, and then we can show you why it's useful. The oxidation number, first of all, of an element in its stable state is 0. So if you have sodium, or you have chlorine gas, or you have P8, which is a stable state of phosphorus, in its elemental form, not combined with anything, All of these have oxidation numbers of 0. In a compound, the sum of the oxidation numbers of the elements in the compound has to be 0. For a polyatomic ion, the sum of the oxidation numbers of the elements is equal to the charge of the ion. For a monatomic ion, the charge on the ion is its oxidation number. So Na plus would have an oxidation number of +1. Sulfide, S2 minus, would have an oxidation number of 2 minus. The oxidation number of group 1 elements is always +1. Group 2 elements is always 2 plus. The oxidation number of fluorine in compounds is always -1. The other halogens are usually -1. And the oxidation number of oxygen in compounds is usually -2. Let's calculate some oxidation numbers here. What is the oxidation number of phosphorus in the salt Mg2P2O7? We want the oxidation number of phosphorus in that salt. How would we do it? Well, first of all, it's a neutral compound, so it has to add, all the oxidation numbers have to add up to 0. Magnesium, we know, is in group 2 in the periodic table. So that means each magnesium is 2 plus. There are 2 magnesiums, so the total oxidation state for all magnesiums is 4 plus. Oxygen, we know, is always -2, or usually -2. There are 7 of them in this compound, so that's -14. That means that for this to add up to 0, the 2 phosphorus elements together have to be a +10, 10 plus, because 4 plus and 10 plus add up to 14 plus to counteract the -14 of oxygen. So each phosphorus is going to be a +5, and that is the oxidation state of phosphorus in this compound. How about the oxidation state or oxidation number of chromium in K2CrO4? Well, K is in the very first group in the periodic table, K+, so its oxidation number is +1 for each one. There are 2 of them, so that's +2. The oxygen is -2 for each one, and there are 4 of them, that's -8. So therefore the chromium has to be +6. And there's only 1 chromium, so the oxidation state of chromium here is +6. That's how you calculate oxidation number. Now, what do you use them for? Take a look at this reaction here. Methane plus oxygen yields CO2 plus H2O. Oxidation numbers can help you understand what's happening chemically here. Let's figure out the oxidation numbers of the various elements we see here. We know that hydrogen is going to be a +1. Hydrogen's always +1. It's in group 1. So that's a +4 for the 4 hydrogen. So the oxidation state of carbon here is a -4. Carbon is -4 in methane. The oxidation number of oxygen here is 0 because oxygen is in its elemental state. Now let's look at the products. Carbon dioxide. Here oxygen is a -2 because it's combined with carbon. And there are 2 of them, that's -4. So the oxidation state for carbon is +4. Now that's interesting, isn't it? Because the oxidation number in the reagent side of carbon was -4, and on the product side is +4. The oxidation state has changed. And for the oxygen, over on this side it's 0, over on the product side each oxygen is -2, right? Because oxygen is in its combined form. So the oxidation state of the oxygen has changed as well. Let's take a look at the nature of the change. Carbon is going from -4 to +4. It's becoming more positive. And when it becomes more positive, that means it's losing electrons. So that's a loss of electrons. And a process in which electrons is lost is called oxidation. Oxidation is a loss of electrons. And if we look at oxygen, it's going from 0 to -2. That is a gain of electrons. And we call a gain of electrons reduction. Reduction. That's a gain in electrons, or a gain of electrons. Loss of electrons is oxidation. Gain of electrons is reduction. There's a couple of mnemonics that students have told me over the years. Oil rig. Oxidation involves loss of electrons, that is. Reduction involves gain. So that's oil rig. Or Leo goes grr. That's a loss of electrons is oxidation, gain of electrons is reduction. So oxidation numbers can help you to see if chemical reactions are oxidation reduction reactions. Here's a question: which element is oxidized and which is reduced in each of the following reactions? Well, okay, here is zinc in its elemental form going to zinc 2+. It's losing electrons. So it's being oxidized because that's a loss of electrons. Loss of 2 electrons. And Cu2+ is going to Cu. In other words, it is gaining electrons. So that's a gain of 2 electrons. And that is going to be reduction. Okay? For H2 and O2, both hydrogen and oxygen are in their elemental form, and they have an oxidation number of 0 for each one. But when they combine to form water, the hydrogen is now +1, the oxygen is -2. So the oxygen has gained electrons, and that's reduction. The hydrogen has lost electrons, and that's oxidation. So that is oxidation reduction, and that is oxidation numbers. And with that, that concludes Chapter 4.